On this example, we're going to look at a closed rectangular box with a square base with sides x and height y. So the goals on this are first create some sort of equation that goes along with the surface area of this box in terms of both x and y. So things to note, it's a closed rectangular box. And what that means is it's going to have both a top and a bottom. All right, the next thing is it has a square base, and they've told us we can go ahead and label our base as x. So drawing a picture always helps when I'm doing these. Really just wraps my head around things a lot better if I'm visualizing it with a picture in front of me. So I've tried to draw one for you. We've got x on the bottom for the sides, and then y is going to be the height of our box. So we have kind of two different components going on here. We have both the base and the top are going to be these squares, where on each of these sides we get an x. Basically, if you can visualize that, it's going to be x times x to get the area of this square or rectangle, however you want to visualize it. So that'll be x squared for that component. Then we have the sides of the box, where the bottom on each one of the sides is going to be an x, but the height on each one of them is going to be a y. So we can represent the area of each one of those sides as x times y. Next, let's put these together and get the surface area function in both terms of x and y. So we have the x squared component, but remember we have both a bottom and a top. So we could say x squared plus x squared, or that's equivalent to 2x squareds. And then we have the sides, which are each represented by an x times y, but we do have 4 sides if we think about going all the way around this box. So we're going to add 4 xy's. So that accomplishes the representing the surface area of this rectangular box. But now we have a follow-up. What we want to do for our follow-up is we're given that if the surface area of this box is 170 square feet, when then we want to find dy dx when x is 5 and y is 6. Okay, so that information, basically we could fill it in. We could say s of 5 comma 6 equals 170. Just going back to kind of how they've represented this, that s stands for surface area. And let's fill in what we can. So what I'm going to do is I'm going to replace the left-hand side here with 170, that fixed value that they gave us. And we could kind of double check our formula if we wanted to, evaluate that function we created by plugging in 5 for x and 6 for our y. It turns out equaling 170. But for our purposes, I'm going to go ahead and replace the left-hand side with 170 and bring along the right-hand side. So 2x squared plus 4xy. Now I didn't plug in 5 for x and 6 for y in this case because all of our variables would have gone away. And remember, the goal on this is to calculate dy dx. So to do that, what I think we're going to have to do is go ahead and take a derivative here. Instead of isolating y on one side by itself, let's do implicit differentiation. And that x equals 5, y equals 6 will come back up in a second. So implicit differentiation, let's get a plan together. All right, on the left-hand side, we just have a constant. So what we can think of there is we can think that is, well, the derivative of a constant is always going to be 0. On the right-hand side, we have 2x squared. Well, we can use the power rule to help us out here. Bring down the 2 from the exponent, multiply it by the 2 in front, and get 4. And then we can reduce the exponent by 1, right? So 2 minus 1 gives us 1 for our new exponent. Now our variable there was x. So if we wanted to, we could put dx, right? We're taking the derivative with respect to x. But when you have the same thing, numerator and denominator, those make a 1. So we usually don't write that part. Next, let's move on to the 4xy. Now, when I look at that, I notice that we have basically 2 functions multiplied together. So if I called the first one the 4x, f, and the y being the second function, g, we can see we have 2 things multiplied together. We're going to have to use the product rule to calculate this derivative. So I'm going to write out the product rule as f prime times g plus f times g prime. All right, I think writing that out always helps out, especially as you're getting used to using all of these rules. with implicit differentiation, so it makes it more of a fill-in problem. So the first component of this is going to be, we need the derivative of 4x. Well, the derivative of 4x is going to be 4, and we could put a dx with that, but we don't need to. And next we copy down our g function, which in our case is y, plus copy down f, which is 4x, but then we need to multiply by the derivative of y. All right, the derivative of y is going to be 1, but remember our variable now is y, so we need to include a dy dx as part of that. From here, it's really a bunch of rearranging and simplifying down to isolate the dy dx on one side if we want to get a function for this, and then we'll come back at the end and plug in the 5 for x and the 6 for y. So to isolate this dy dx on one side, we're going to have to move that 4x to the other side. Because it's positive, we'll go ahead and subtract 4x from both sides. We need to move that 4y to the other side. So again, we'll subtract it from both sides. This will allow us to say positive 4x minus 4x makes 0 x's. Positive 4y minus 4y makes 0 y's, as we kind of combine those like terms. So this will be 0 minus 4x minus 4y on the left-hand side. And then let's think, what do we still have on the right-hand side? We still have 4x, and then what we really care about, that dy dx. I did drop the multiplying by 1 there out in front of the dy dx. Okay, so all that really remains here is we need to get rid of that 4x from the right-hand side. Well, right now that's connected with a multiplication, so we use division to get rid of it. So we want to divide the right-hand side by 4x. And it looks to me like the simplest way to do this on the left-hand side would be divide each individual term by 4x. Okay, so 4x divided by 4x makes a 1 in front of our dy dx on the right-hand side. And then on the left-hand side, let's think about simplifying this down. Well, we have 4 over 4, which makes 1, x over x, which makes 1. So what remains over here for that first fraction is going to be a negative 1. Then simplifying the second fraction, well, 4 over 4 makes 1. So we can eliminate those. And we're going to be left with minus y over x. So that's a nice formula for our dy dx, or the derivative of y with respect to x. All right, to finish this one up, what we're going to do is go back up here where they said use x equals 5 and y equals 6, and we're going to plug those values in for our x and y. So down here, let's replace, remember we said this is going to equal, well, negative 1 minus, we said 5 for x and 6 for y. All right, all that remains here is, let's go ahead and do a little bit of simplifying. We can rewrite that negative 1 with a common denominator of our other fraction as negative 5 over 5, means the same thing as negative 1, minus 6 over 5, just carrying along that second fraction. Combine our numerators, keep the common denominator, and there we have dy dx. For this specific case, that's going to be our solution. So I hope this helps out as you're working on first creating a function to represent the surface area of a box, and then going ahead and using implicit differentiation to help you solve down. Good luck.